The light from sources like the sun or an incandescent light bulb do not show single plane polarization. Let us represent light using the E vector and its propagation as shown. The light from these sources is composed of many directions of the E vector distributed randomly around the direction of propagation of light. This light is transverse but unpolarized. An unpolarized light can be converted into a plane polarized light using Polaroids. A Polaroid consists of a long chain of molecules aligned in a particular direction. The components of the electric vector of the incident light, which are in the direction of the aligned molecules, get absorbed. The direction perpendicular to the direction of aligned molecules is known as the pass axis. That means the pass axis of a Polaroid is the polarizing direction. If an unpolarized light wave is incident on a Polaroid, the Polaroid sheet transmits only that light which has its electric field vector vibrating parallel to pass axis and absorbs the light with E vector vibrating at right angles to pass axis. Now, consider a Polaroid sheet placed in the path of a plane polarized light. The vector E shows the plane of vibration of the light incident on the Polaroid sheet. If EY and EZ are the components of E, such that EY is parallel to the pass axis and EZ is at right angles to it, then only the EY component passes through the Polaroid sheet. Now allow light from an ordinary source to pass through the Polaroid P1 and incident on a screen. It is experimentally observed that the intensity of the polarized light transmitted through the sheet is half the intensity of the incident light. Rotating P1 has no effect on the transmitted beam and transmitted intensity remains constant. This can be explained as follows. In an unpolarized light, the direction of the E vector is randomly distributed around the propagation of light. We can resolve these different vectors into components EY along the polarizing axis and EZ perpendicular to the polarizing axis. If the intensity of the incident light is 2I0, then, because of symmetry, the intensity of light in the direction of the polarizing axis is I0 and the intensity of light in the perpendicular direction is I0. The Polaroid allows only the EY component of the incident light to pass through it, and hence the intensity of the transmitted light is half the intensity of the incident light. Let the intensity of the plane polarized light transmitted by the Polaroid P1 be I0. Now, place another Polaroid P2 between the first Polaroid and the screen in the path of the plane polarized light of intensity I0. The intensity of the light falling on the screen depends on the orientation of the Polaroid P2. If we start rotating the Polaroid P2, the intensity of light incident on the screen reduces to nearly zero at one position and reaches its maximum when turned by 90 degrees from the position of zero intensity. This can be understood by considering the orientations of the pass axes of the two Polaroids. The light passing through the Polaroid P1 gets polarized along its path axis. If the path axis of the Polaroid P2 is perpendicular to the path axis of the Polaroid P1, then no light is transmitted through the Polaroid P2. If the path axis of the Polaroid P2 is parallel to the path axis of the Polaroid P1, then the entire light transmitted by the Polaroid P1 is also transmitted by the Polaroid 2, and hence the intensity is maximum. If the path axis of P1 makes an angle theta with the path axis of P2, then the component of E parallel to the path axis of the Polaroid P2 is equal to E cos theta. If Em is the amplitude of the light incident on the Polaroid P2, then its intensity I0 is equal to Em squared. The amplitude of the light emerging from the Polaroid P2 is then equal to Em cos theta, and the intensity of light I emerging from P2 is equal to Em square cos square theta. This can also be written as I is equal to I0 cos square theta.